and welcome to New Scientist Weekly, your one-stop shop for the most fascinating science and technology news. I'm Christy Taylor in New York.
And I'm Timothy Revel in London. This week on the podcast, we will finally get an answer to why the science on consuming alcohol is just so confusing. Plus, a breakthrough towards creating the heaviest element ever in the lab. And why green plastic is, unfortunately, not so green.
But first, we're taking a deep dive into the Pacific Ocean, 5,000 meters down to the sea floor. We're in a part of the Pacific called the Clarion-Clipperton Zone. It's between Mexico and Hawaii, and it's noteworthy because the seafloor here is covered in millions of rocks about the size of potatoes. These rocks are called polymetallic nodules, and you may have heard of them because they contain valuable metals needed for batteries: cobalt, lithium, manganese, and nickel. Multiple companies have high hopes to mine them in the not-too-distant future. But researchers have now discovered that there's something very, very special about these rocks, and it's potentially crucial to the ecosystems that they're in. Environment reporter Maddie Cuff is here to tell us more. Hey, Maddie.
Hello.
Okay, Maddie, I've been seeing these findings called amazing, unbelievable, shocking. So what's going on with our potato rocks?
Yeah, can I add jaw-dropping to that pile, please? So as you said, these metallic nodules that we've got on the seafloor are already special to us because of their high metal content. But it turns out they're not just lumps of passive rock. Researchers have just discovered that these nodules are in fact producing oxygen on the seafloor. That is such a surprising finding. The researcher involved who made the discovery, it's a man called Andrew Sweetman, was so surprised, in fact, that he completely discounted his findings for 8 years. Back in 2013, he started measuring how much oxygen was in the water in areas of this deep seabed called the Clarion-Clipperton Zone. He essentially was sealing off small test areas, and he assumed that the oxygen in these sealed areas should steadily decrease in them over time. But to his surprise, oxygen levels on the seafloor were actually increasing. He was so startled by those findings that he just assumed his equipment was faulty.
Right, because this goes against most of what we know about where oxygen comes from, right?
Yeah, exactly. Before this discovery, we thought that oxygen in the ocean was produced only through photosynthesis, which obviously requires sunlight and plants. Now, no sunlight hits the seafloor in the deep ocean because we're thousands and thousands of meters down, and there aren't really any plants either. So if oxygen levels are rising, it suggests there's an alternative source of oxygen that could be supporting deep sea ecosystems, one which we've only just discovered.
The deep ocean is so mysterious, and that the rocks may be the ones producing oxygen down there, not plants. That's just really quite mind-blowing. It's so exciting. And I can understand why it took a while for anyone to really take this seriously. So you mentioned that Sweetman, he just wrote this off as a kind of dodgy reading from faulty equipment, maybe from 8 years ago. What happened to change his mind?
Yes, so as we were saying, he started doing some of this research back in 2013, and he kept sending his machines off to the labs to get tested. They kept saying there's nothing wrong with them, but eventually he just let it lie for a bit. But he was back on a research cruise in the Clarion-Clipperton Zone in 2021, and again he started measuring oxygen levels on the seafloor and had a chance to kind of redo some of those experiments. And again, they showed rising oxygen levels on the seafloor. So they just decided to start looking into it. And after testing and retesting and fiddling with the machines and trying different measurement techniques, they finally realised that they were probably onto something. So they began to try and figure out where the oxygen could be coming from. They took lots of samples on the seabed, effectively by sealing off a 22 centimetre square of water and sediment to measure the changes in oxygen levels. They also took some of these nodules and sediments back into the lab and began to rule out possible causes of oxygen production, which included some quite cool experiments that involved poisoning their samples to kill any potential oxygen-producing microbes on there, as well as testing them for radioactivity. But in actual fact, what they think is happening is that these nodules are effectively acting as mini batteries.
Wow, that's very cool, mini batteries. I mean, they do have all the metals that they might need, as you said, but how does that actually work?
Exactly. They've got pretty much everything in them that you would want to create a battery, so it kind of stands to reason. The idea here is that the rocks are acting as kind of geobatteries, natural batteries, and they are creating a current that runs through them that will effectively split seawater into hydrogen and oxygen. Now, experiments in the lab by Andrew and his team measured the voltages on the surface of each of these nodules, and they found it to be almost equivalent to the voltage in a typical AA battery.
Wow.
So if these rocks were clustered together enough to join forces, there would probably be enough voltage to power this electrolysis, this splitting of seawater into its component parts. And then that would explain the elevated oxygen levels.
This is all so amazing. And I just want to take us to sort of the fact that these rocks sit in an environment, in an ecosystem. And I'm wondering then if the oxygen from the nodules would be enough to provide oxygen for deep ocean animals and other life forms then.
Potentially, yes. That's one thing that these scientists really now need to figure out is how much oxygen is being produced, because there are still a lot of unknowns. We don't really know, like I said, how much oxygen is being produced, because we don't know if these geobatteries work all the time or if they only work sporadically. We also don't know where the energy is coming from to create that current in the first place. And we don't know whether the oxygen will be produced if, say, the nodules are covered in sediment.
A lot of unknowns, as you say, but also perhaps not a lot of time. There are deep-sea mining companies eyeing up these nodules for their metals already. And that's controversial. It's not that everyone agrees that that's what they should do, but there's potentially a big impact on ocean ecosystems if they go ahead. This new research seems to really turbocharge those discussions.
Yeah, I mean, it definitely adds fuel to the argument that we really don't know enough about the ecology of the deep ocean to understand what harm we would be doing if we started scooping up these nodules. I mean, for one thing, the sediment spray from these deep ocean mining machines could hugely disturb habitats and maybe even smother the nodules that are left on the seabed and stop them producing oxygen, for example. Plus, if it turns out that these ecosystems are really relying on the nodules for their oxygen, well, you can kind of see how it might be quite damaging to remove them.
I feel like this prospect of deep-sea mining has been on the horizon for some time now, but it's not actually quite here yet, right? Nobody's really doing it in earnest.
Not quite yet. Countries are still wrangling over whether to allow deep-sea mining in international waters, and if they did, what rules companies would have to obey. There are some mining companies that have submitted some applications to start mining, but as I say, that red tape needs to be ironed out before that can start happening. And there's a growing movement to prevent it all happening at all. So far, 27 countries and some companies have backed an all-out moratorium on mining until we know more about what's going on in the deep ocean. There's one more twist to this already pretty extraordinary story. To prove their environmental credentials and demonstrate that deep-sea mining could be done safely, some of these mining companies have funded quite a lot of scientific research into these nodule-rich regions of the ocean. And in fact, Andrew's discovery was part funded by one of these deep-sea mining companies, which, given that his findings could seriously harm the prospects of mining ever taking place in the deep ocean, is awkward, to say the least. And maybe most awkwardly, that company now says that they're in the process of writing a rebuttal to Andrew's research, which, again, they funded.
Wow. Be careful when you go digging. You don't know what you're going to find.
Exactly.
Amazing. All right. Thank you very much, Maddie.
Thank you.
Now, it's no secret that alcohol research is, well, at best, a bit confusing. A couple of decades ago, much to many people's delight, the prevailing view seemed to be that drinking a little is actually quite good for you, with claims that it reduces the risk of heart disease. Moderate drinkers actually live longer, so said the research. But in recent years, researchers felt a bit more like the morning after the night before, with that actually changing quite a bit, and now suggesting that any level of alcohol may not be safe at all. Well, reporter Michael LePage is here to explain what's going on. Hi, Michael.
Hello.
Can you help us make sense of all of this? Is a bit of alcohol good for us or not?
Not, I regret to report. Yeah. It's been clear for many years that there are some serious flaws in the studies claiming that drinking it a lot has benefits, flaws that might bias their conclusions. So researchers have been trying to do more rigorous studies that address these potential biases. Now, the new thing this week is there's a meta-study out that's analysed 107 different studies. So what the team did is look at the methods that each study used, and they said, did these methods avoid these potential sources of bias? And out of those 107, they found that just 6 studies had done this. And all of those 6 studies found there was no benefit at all to drinking a little. In other words, even moderate drinking probably shortens your life rather than making you live longer.
I can think of some benefits of drinking a little, but maybe not ones this study was looking at.
In health terms, we're talking,
yeah.
yes, absolutely, there are other benefits.
When you say that these studies had potential biases in them that weren't being accounted for, what sort of biases are we talking about? Can you just explain that a bit?
Yes, so to work out what effect drinking has on our health, what we want to do is compare people who have never drunk with people who do drink varying amounts. But what a lot of these studies have in fact done is lump together people who have never drunk with people who've stopped drinking. And of course, people who stop drinking often do so because they have health problems. So then if you compare moderate drinker with people who have health problems, the moderate drinkers appear healthier. And that's one issue. And then another related issue is that many of these studies use very loose definitions of never drinking. So for instance, there was one study where they defined people as lifetime abstainers, even if they drank on up to 11 occasions every year. That's definitely not what I would regard as abstaining.
Yeah, it's not exactly a lot, but once a month is definitely something. So you're saying most studies have got it completely wrong then?
Well, I think, to be fair, all of these studies have concluded that drinking a lot is bad for you. So that big picture hasn't changed at all. What we're talking about here are the effects on your health of drinking a little, like a glass of wine or beer a day. And they're the changes from there being a small benefit to a small risk. So I wouldn't say these studies have got it completely wrong in the past, but I think psychologically, this is a very big shift in the way we perceive drinking.
But does this mean we should all stop drinking entirely?
Well, that, of course, is a choice for each of us to make, but it should be an informed choice. What these more rigorous studies are showing is that there's a linear relationship between the amount we drink and the risk of dying of any cause at a particular age. This means that the risk is small if you only drink a little, and it rises and rises the more you drink. Of course, this has to be seen in context. So Tim Stockwell, who did this meta-study, says that the risk of moderate drinking is relatively small compared to some of the other things that we do. But nevertheless, he thinks it's important that people are made aware of it. In fact, he thinks there should be warning labels on bottles. So that's going to go down a storm with the drinks industry. But personally, I think he's got a point.
Yeah, I'm sure people who sell alcohol would love to have like a big skull and crossbones on the front of their bottles. Thank you, Michael.
Thank you.
Time for a quick break to tell you to listen to some other fun stuff from the team at New Scientist. If you've ever wondered how quantum physics applies to our lives, relationships, and even to global conflicts, then we've got you covered with an interview with physicist Carlo Rovelli.
It's easy to think relationally if you think that there is a relation of something basic down there. But in quantum mechanics, the thing itself doesn't seem to have any property at all, except for the fact that it's affecting something else. So the indication here is that a property of an object is not something that pertains to the object itself, is a name we give to the way this object interacts with something else.
That's coming up on Tuesday. Stay tuned for that.
And also, we share a lot of fun stuff with you every single week, but we also appreciate when you share your thoughts and curiosities with us, and we've got a chance coming up. We will soon be interviewing psychologist Lucy Folks about her newest book, Coming of Age. It's all about adolescence, what science can tell us about the lives and behaviors of teenagers. We will get behind the stereotypes, bust some myths, and dig into what the last decade of research is revealing about this critical age.
And we want to help answer your questions. Do you have teenage children? Are you a teenager? What do you wish you understood better about adolescent behavior, emotions, or even social situations? Or are you trying to make sense of your own teenage years? Could be dangerous, however long ago that was. Send us an email to podcasts@newscientist.com with any of those questions, or even better would be for you to record us a short voice memo on your phone and email us over that. And that address again, that's podcasts@newscientist.com.
Next up, we are going on another field trip. But instead of the deep sea, we are visiting a relatively unexplored but very exciting corner of the periodic table of elements. Don't worry if you can't remember the details. Just imagine in your mind the lower right corner, which houses rare, radioactive, super heavy elements. And researchers are now getting closer to making the long elusive element 120. That element would have 120 protons and be the heaviest element ever made. And its name is unbinilium. Our stalwart guide on this field trip is, as you might have hoped, physics reporter Carmela Padovich-Callahan. Hey, Carmela.
Hello.
All right, heaviest element is definitely not a joke. So what's the backstory? Give me some lore.
There's actually a really long history of folks trying to make element 120, and most of the attempts have not gotten very close. To make a heavy element like element 120, you have to keep adding particles into the nucleus of that element. And this usually makes the nucleus less stable and harder to control. So you're kind of like piling on more and more stuff, and the more stuff you have, the more likely it is to fall apart. So how you do this in the lab is like, of course, you can't just like hold an atom and pile stuff into its nucleus. You actually smash stuff together. You take two relatively heavy elements, which are unstable, and you crash them into each other and hope that in that crash, you will get a third heavier, also unstable thing. So it's really difficult business to take charge of all of this and also to detect what's actually happening as you have all these smashes and decays. And the last time we did this successfully, the last time we added a super heavy element was in 2002 when researchers in Russia made element 118. But the method that they used hasn't been successful in going heavier. Now, researchers at Lawrence Berkeley National Laboratory in California have found a way to make element 116, which is called livermorium. And they think that the recipe they use to make livermorium is the one that will get them to element 120.
Okay, so they've not yet hit the magical number 120, but they see a path to it. So what's this new method? How is it going to get them there?
Yeah, exactly. So the big change that they've made is that they are using a beam of charged titanium atoms. And this has never been done before. So they're taking titanium, they're vaporizing it, they're ionizing it, they're putting it into an accelerator, and they're smashing it into a target made of plutonium to get element 116. And it was sort of unclear whether you could use titanium for this. Before, they were using an isotope of calcium, which was known to be better behaved. But now they've sort of done a proof of principle experiment to see that titanium works. And that's sort of the big change that we're reporting on here.
So they just smash the atoms together and that makes 116? Is it that simple? Is it that quick?
Well, it took 22 days to make two atoms, and that may sound slow, but it's actually quite fast. So when I spoke to one of the researchers, she told me that they saw the first atom on day 8, and they were sort of shocked by that because they were trying to not keep their hopes too high. And then towards the end of the run, they saw the second atom, and that shocked them even more because they were like, wow, managed to do 2 in the 22-day run. That is very different than what had been done in the past, where it could take hundreds of days to detect just a single atoms.
Yeah, it's one of those sort of physicists seeing things slightly different moments where producing just 2 atoms over the course of 3 weeks is considered actually quite quick. So what makes them think this approach is the one that's going to lead to element 120?
The big thing here was to make sure that the titanium beam would actually work. And now that it does, they just have to switch out the target. So to make element 116, they use titanium beam smashing into a target made of plutonium. To get to livermorium, they have to swap plutonium for californium. Californium is even heavier and even more radioactive, so something else new that has to be tested, but getting the titanium beam gives them hope that this final swap on the target will be exactly the thing that gets them to 120.
Oh, that's so exciting. So we have a recipe. It's time to move forward. When can we expect our, single atom of element 120 to appear in the lab?
Yeah, it's always extremely tricky to make any sort of prediction, but the Lawrence Berkeley folks told me that they have solid plans to start the next experiment in 2025, Whether it will take another 22 days or a couple hundred days is much harder to say. But basically, once the Californian target is ready and it's already being made, they will just sort of turn the machine on. And hopefully we talk about this again in a year or year and a half, and I have something to say.
A year plus 500 days, maybe.
Yeah, exactly.
Next up, we've got some kind of disheartening news that our attempts to be more environmentally friendly may actually sometimes do more harm than good. And it may seem paradoxical, but biodegradable microplastics appear to hurt soil and plant health more than the regular kind of forever plastic stuff. So to explain this quite strange finding, we've got assistant news editor Alexandra Thompson. Hi there, Alex.
Hi there.
So talk us through this one. What's actually been discovered? What did they find out? How did they go about it?
Right, so it's an early stage study, but it's definitely an interesting one. So basically, researchers in China collected soil samples from around the university where they work, and there were no obvious signs of plastic in these soils to begin with. So then they put the samples in pots, and to some of them they added conventional microplastics made up of polyethylene, and to others they added biodegradable microplastics, which are sometimes called biomicroplastics. And then in both, they attempted to grow wheatgrass, and they also grew it in unaltered soil, which acted as another comparison. And then they waited to see how the different groups of wheatgrass fared and took measurements of the soil chemistry.
Okay, so we've got bioplastics and the non-bioplastics, and we're seeing how the plants do. What did they find out?
So after just 10 days, the biomicroplastics had significantly reduced key minerals such as nitrogen in the soil. And the soil with the biomicroplastics also had lowered microbial diversity. And maybe not surprisingly, bearing in mind those two details, the plants in those pots were also stunted compared to the one grown in the unaltered soil. So the pots with the regular microplastics, they also had less nitrogen, microbial diversity, and some plant growth stunting, but the effect was less dramatic than in the biomicroplastic soil.
Wow, that's really not a result I would have expected. Do we know why the biomicroplastics had this effect?
We don't know exactly why. I mean, that's a sort of question that will need more research, but there's possibly something in the chemistry of biomicroplastics that really reduces nitrogen levels in soil, and that then may hinder a plant's ability to make chlorophyll, which is the green pigment that helps them absorb energy from the sun. I should also add that weather conditions may also make a big difference. So when the researchers simulated a flood by adding excess water to the pots, they found that this made the biomicroplastics have an even greater negative effect. So the plants were even smaller. And it's possible that's because the extra water was encouraging pathogenic bacteria in the soil that then made conditions even worse for the plants.
This is all quite disappointing. I mean, sometimes you try to do something good and you end up doing something bad. But surely this is just one quite specific study. We shouldn't wash our hands of biodegradable plastic completely from this, should we?
No, not at all. So this is a short study. So even though the results became clear at day 10, the whole experiment lasted 100 days. So we don't know anything about the longer-term effects of different types of microplastics here, and the researchers haven't speculated on that. So I think it's just a sign to do more research and really carefully consider the use of any type of plastic, especially when fragments can find their way into almost every part of our environment, not just soil.
Yeah, maybe that's the thing. We've got to be careful about keeping these plastics out of the environment. All right, thank you very much, Alex. Christy, I've got some big news for you from the world of mathematical AIs. In fact, I think it would be fair to call this new AI the most advanced AI mathematician yet.
You know, I didn't know that we had a lot of AI mathematicians in the first place, but, is this guy better than humans?
Yeah, it's something people have been working on for quite a long time, but funnily enough, they're still not better than humans. I think maths is one of those really interesting problems for AIs because obviously the very first computers were entirely about mathematics, and if you learn how to build a simple computer circuit, one of the first things you'll do is build a circuit that can add two numbers together. And calculators, they're obviously way better at arithmetic than humans, but AIs like ChatGPT and other large language models, they really struggle with even basic mathematics, like the same kind of mathematics that a calculator can do.
That's so funny that they're not good at math despite being literally made of math. All right, so what can this new one do that is still not quite as good as a human?
Yeah, so this new AI, it's built by Google DeepMind, and it's called Alpha Proof. And it's managed to nab a silver medal at the International Mathematical Olympiad, which is this big competition for mathematicians, for young mathematicians. And it's the first time an AI has ever managed to win a prize there.
Okay, so the IMO, that's really tricky math problems, right? So proofs with logical arguments, right?
Yeah, that's right. And I think what's most interesting here is the method by which Alpha Proof works. So you need language abilities to even pass the problems in the Olympiad because they're complicated, they've got different steps to them. But large language models like ChatGPT, they aren't reliable mathematicians. You can't trust them to follow simple logic. So what DeepMind has done is they've combined two AIs. They use Gemini, which is Google's large language model, and then there's another AI that is better at the logic stuff, and that's the one that's involved in actually constructing proofs. So it's obviously not got to a gold medal standard yet, but I think the development suggests that milestone is not too far away and just starting to seem inevitable. And personally, as you know, my background was in mathematics and, then wrote a lot about AI. So I'm so excited to see what happens next here. I feel like a real mathematical breakthrough is just around the corner for AI, and there are so many interesting, long-standing problems in mathematics that we don't know how to crack. Maybe AI could be the tool to help us get there.
All right, I'm happy for the mathematicians out there. I've got some bad news, though, for you this week.
Oh, yeah.
Speaking of AI, there's a new way people with the right technology can intercept your private information, and it's probably already being done in the real world. And again, you can thank AI for this brand new thing to be anxious about.
I feel like these kind of new ways to steal information, they're always quite cunning, but kind of impractical. What's this new method? Talk me through it.
Well, if you ever use an external computer monitor to connect to your laptop, one way you might do that is with an HDMI cable. These cables transmit digital data, but like any signal sent through a wire, there's a certain amount of electromagnetic leakage that sort of, gets out between one computer and another. So back when we used analog cables, reading this leakage was really easy for hackers. The transition to digital signals, which are more complex, made all of that much harder until AI. And a team in Uruguay has now managed to demonstrate that if you use a sensor or antenna to intercept the leaked HDMI signal, a properly trained AI model can reliably reconstruct the images from your computer screen.
So images from a screen, that could be a lot of stuff. That's like my bank login details, my emails, passwords, all my boring WhatsApp conversations that maybe I wouldn't want someone snooping on. That seems like a lot.
Yeah, so that is a lot. And would-be hackers could theoretically do this from several meters away from you. So they wouldn't even have to be in the same room as you, though. Speaking of impractical, when I say antenna, I mean you'd have to be like literally standing outside a building holding one, unless you can find a way to plant a recording device of some kind that can transmit the data later. So I do want to say that while the researchers suspect this might already be happening in very sensitive settings like industrial or government facilities, regular users of computers probably don't have much to worry about or, nothing more than the usual fears we have of our data getting leaked and sold.
Yeah, just those. But on this particular one, we can sigh a sigh of relief. All right, well, one final one I've got for you from Space News, and that's that we've got some new insights into the powerful blasts of radiation called gamma ray bursts. And this story has really got everything. It involves the most powerful explosion in the universe since the Big Bang, finding a signal that scientists think shouldn't exist, and antimatter copping the blame.
Wow. Okay, so that's a lot to talk about. Can you give me the rundown? What's going on?
Well, let's start with the fact that gamma ray bursts are, as a category, the most powerful blasts of radiation in the universe. And while we don't know exactly what makes them, scientists suspect that the biggest ones come from when stars collapse and form black holes. The black hole then creates a kind of jet of material which moves close to the speed of light, and that jet pierces the remains of the star and sends out this huge blast of radiation that we can then see from Earth. But there is a but here. We don't know how this radiation is produced or what's actually in that jet of material. With other light sources in the universe, we can look at a thing called spectra, which is basically a pattern of frequencies where the signal is stronger or weaker, and that pattern gives us information about the atoms or matter that produce the light. But gamma ray bursts, they seem to have this smooth, featureless spectra, which is weird. But here, in this new research, when they looked a bit more closely at one particular gamma ray burst, they saw something different.
Is this where the biggest explosion in the universe comes in? Because I don't want to forget about that.
Yeah, that is where it comes in. And that would be the gamma ray burst that's got the fantastic name BOAT, the brightest of all time, which I absolutely love, and was discovered in 2022 and is so far the brightest gamma ray burst we've ever seen. So with this research, a team in the Netherlands found that the spectrum from the gamma ray burst, known as BOAT, in fact did have a distinct peak at a distinct energy level. And that has scientists extremely excited. They're saying this could be one of the biggest surprises in this field in a decade, as that could help tell us what it's made from.
That's super exciting, right? So we found a peak in the spectrum for a gamma ray burst, never found one before. What did we learn then from this peak about the process that made this gamma ray burst, that black hole, the jet of material, the source of energy for this huge burst of radiation, all those things? You did mention antimatter.
I did, and we get to the third act. So first off, this data suggests that the jet from the black hole was so energetic that it didn't contain complete atoms, which leaves us with a scenario where antimatter was colliding with regular matter, which annihilates both. And this would have produced gamma rays, like what we see in a GRB. They also figured out that the jet was moving at 99.99% the speed of light, so incredibly fast. Now, adding this all up, it's only because this particular GRB was so powerful that we could actually figure any of this out. But now that we have, researchers are really excited to look for lines of spectra in other weaker gamma ray bursts. Though they may end up being more difficult to find, they might also reveal more about these amazing blasts of energy.
This is where I want to say, so what we need is a bigger boat, is what you're saying. That's it for this week. If you like this show and think more people should know about us, please do give us a 5-star rating or even a review on Spotify and Apple Podcasts. It really does help bring us to more earballs.
We've got more fascinating stories from New Scientist on our website at newscientist.com, which you can read in the normal way, or of course from standing outside someone's house using a big antenna and a properly trained AI model. We'll be back next week, but that's bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.